Enhancing the structural performance of column using GFRP rebar and hybrid fiber. Abstract glass fiber reinforced polymer, GFRP, rebars is a proven and successful alternative reinforcement that will give structures a longer service life as well as non-corrosive material properties. In this present study, an experimental study on columns with hybrid fiber and GFRP rebars was performed. Their performance was evaluated by comparison with a conventional steel reinforced column. 6 hybrid columns with fiber and GFRP rebar and 3 conventional concrete steel reinforcement columns were cast and tested under different eccentric 0,0, 0,25, 0,50 loadings. The fibers used were steel and glass fibers, which improves the concrete strength property. Tests were done to check the load carrying capacity of columns for both axial and eccentric loads, deflection and buckling nature of column. The GFRP rebars were able to withstand the peak concentric and eccentric loads without crushing and local buckling. Also, after load removal, deflected GFRP column regained its original position and crack width also reduced. In steel reinforced column, steel rebar were yielded column, and after load removal, no deflection regain and crack width reduction were found. The performance of HYFC rebar was 18% greater while considering to that of conventional concrete column. Keywords: elastic instability, GFRP, hybrid fiber, load carrying capacity. Introduction. General. Columns are important structural members which carry the load from the beams and upper columns to transfer the ground through foundations. Column failure can cause elastic instability due to load carrying capacity of RCC columns reduced drastically for actual cross-sectional area and percentage of reinforcement steel, crushing failure due to high axial load compared to cross-sectional area of the members causes the RCC vertical member is crushed failure or material failure. The most popular drawback for corrosion steel reinforcement due to aggressive environments, voids present in RCC member, coastal regions that cause weak tension strength of reinforcement, hence failure of columns. Glass fiber reinforced polymer, GFRP, rebar is a satisfying replacement or auxiliary for this condition because of its high tension strength, 1600 MPa, non-corrosive characteristics. ACI 440-1R06 reported in the U.S. typical uses GFRP rebar to constructed bridge deck, in 1997. FRP composite material consisting of continuous fibers impregnated with a fiber-binding polymer then molded and hardened in the intended shape. Hybrid, a combination of 2 or more different fibers, such as carbon and glass or carbon and aramid, into a structure. In this present work was to investigate structural behavior of columns, load vs deformational character, load carrying capacity for different eccentric conditions, spiffiness of the HYFRC column with GFRP compared the conventional steel reinforcement column. Hybrid fiber used to enhancing the concrete strength properties and prevent the crushing failure or material failure. Hybrid fiber. Fibers are mostly used for special requirement only. The fiber used in concrete to increase the concrete strength properties and prevent the shrinkage, crack, bleeding of water, etc. Different type of fiber such as glass fiber, coconut fiber, glass fiber, polypropylene. A composite can be termed as hybrid, if 2 or more types of fibers are rationally combined in a common matrix to produce a composite that derives benefits from each of the individual's fibers and exhibits a synergetic response. GFRP rebar. Glass fiber reinforced polymer, GFRP, rebar is sold bar which contain of thinnest glass fiber embedded in a polymeric resin matrix and additives. The major cause of deterioration among reinforced concrete structures is corrosion of the reinforcing steel. Among others, one viable option is to reinforce concrete with glass fiber reinforced polymer, GFRP, bars, a non-corrosive material. GFRP reinforcing bars are made primarily of glass fibers. Being non-corrosive, GFRP bars can help extend the life cycle of reinforced concrete structures substantially, as well as reduce their maintenance, repair, and replacement costs. While GFRP is becoming a viable reinforcement alternative, it presents design challenges which are different than those in the design of conventional steel reinforced concrete. 2. Material used 0.75%, volume of cement. 0.75%, volume of cement. A. Cement. Ordinary Portland cement conform to IS 10262 to 2009 JSW cement 53 grade produced from single source was used. B. Fine aggregate. Locally available river sand was used as fine aggregate which passes through 4.75 mm sieve as per IS 383-1978. C. Coarse aggregate. Locally available coarse aggregate was used as coarse aggregate which passes through 20 mm to retain 12.5 mm sieve as per IS 383-1978. The specific gravity of the coarse aggregate is 2.74. D. Water. Potable water which is available in laboratory is used for casting and curing of specimen as per IS 456-2000. W/C.45 was in mix. E. Steel fiber. Defined as short, discrete length of steel fibers with an aspect ratio 20:100 with different types of steel fibers is used for concrete reinforcement. Round fibers are the most common type and their diameter ranges from 0.25 to 0.75 mm. Rectangular steel fibers are usually 0.25 mm thick. E. Glass fiber is a material consisting of numerous extremely fine fibers of glass. Glass fiber thinnest fibers are the strongest because the thinner fibers are more ductility. GFRP rebars. GFRP fiberglass and composite material consisting of continuous fibers impregnated with a fiber binding polymer then molded and hardened in the intended shape. Non-corrodible, high tensile strength, low weight compared to steel. Different diameter is available 6 mm, 8 mm, 10 mm, 12 mm, and 16 mm. 3. Test program. The test program consisted of 9 concrete columns measuring 150 mm x 150 mm x 1000 mm cross-section. The test column could be specified as a short column because the slenderness ratio, L/D, of the specimens was less than 212, that is, less than 22 based on ACI 318 to 1424. The tested specimens were divided into 3 groups, as shown in Table 1. Each group consisted of 2 concrete columns with the same reinforcement details but tested under different eccentricity conditions of 0, 25, and 50 mm, equal to 0, 0, 0, 25, and 1, 50, respectively. The specimens were identified on the basis of the longitudinal and tie reinforcement material, steel or GFRP, diameter of the longitudinal bar, tie spacing, and eccentricity amount of the applied load. For example, specimen G10T150E 0.0 is reinforced with GFRP bars and ties. 4 10 mm diameter bars were used as longitudinal reinforcement, tie spacing was 150 mm, and it was tested under concentric load. The first group, S10T150, reference specimens, consisted of 3 concrete columns reinforced with 4010 longitudinal steel bars and 06 steel ties placed at a spacing of 150 mm. The columns in the 3 other groups were reinforced with GFRP bars and tie. The dial gauge was positioned at mid-height to measure the lateral deflection of the column during the loading stage. 4 test results. A cube test result. Compressive strength is the maximum compressive stress that, under a gradually applied load, given solid material can sustain without fracture. Compressive strength is calculated by dividing the maximum load by the original cross-section area of the specimen in compression test. Cube test result mentioned below in Table 9, 7 days test. B. Experimental test results on the column load carrying capacity. The section discussion for test results of steel reinforcement RCC column and HYFC with GFRP rebar RCC column. All specimen were tested under the different eccentric, 0, 0, 0, 25, 0, 50, load condition. They failed and there reached maximum load carrying capacity. The moment and stiffness are finding as the maximum load vs horizontal deflection at maximum load. The results are show table, 10. Conclusion. The following conclusions were drawn based on the experimental investigation on eccentric behavior of column. The load carrying capacity of eccentricity, 0, HYFRC column with GFRP was found to be 18% greater than the value of conventional concrete column. The maximum deflection noted at their ultimate axial load in the GFRP rebar and normal steel reinforcement column are 1.45 mm and 1.3 mm respectively. Percentage of eccentricity increase in GFRP column is very similar to behavior of conventional reinforced column. All eccentric loaded GFRP columns showed no rebar failure and the column top compression zone crushing failure occurred. Hybrid fiber performed well with increase in compressive strength and prevention of fine cracks. The moment carrying capacity GFRP column was 5% higher than the steel reinforcement column. The increase of eccentricity of GFRP column decreased the stiffness compared to axial stiffness. The GFRP column with increase in the eccentricity without local buckling or elastic instability. GFRP column had large deflection capacity without failure compared to steel reinforcement column.